So the nice thing about writing these in exponentials is that we can pull this term out of this, and this, because exponential of the summation is actually the product of respective exponentials, right? So let's pull this exponential out of everything. And let's just erase this because we already know this, just to make space for my calculation. So okay, so this is now equal to imaginary part of 1 over delta x squared. The common term is e to the j 2 pi I delta x, and the uncommon term is e to the j 2 pi k delta x plus e to the minus j 2 pi k delta x minus 2. Agreed? Yes, I missed the k in the first term, 2 pi k, yes. Okay, so what is this part? What is the summation of these two exponentials minus 2? Well, what is the summation of these two exponentials? Well, each exponential is a cosine plus j times a sine, right? The sine part actually cancels, because 1 is plus, 1 is minus, and sine is an odd function. The one that remains is the cosine, because cosine is an even function. So they actually add up to the same thing. So this part is basically 2 times cosine of 2 pi k delta x minus 1, right? All right. So that's a real number that comes out of this linear superposition of complex numbers. And now the only complex part is the first part. And the first part is actually just the wi, right? Okay, so the whole thing computes out to be 1 over delta x square wi, because the imaginary part of this is wi, right? And then times 2 cosine 2 pi k delta x minus 1. Okay, so let's pause a little bit and think about what's the consequence of what we have derived. I mean, the algebra is actually not that important as long as you know how to do that. What's important is actually the consequence. The consequence is that no matter if you use a finite difference operator to approximate the differential equation, or you use an analytical function, analytical derivative, as soon as you plug this into the differential equation, what you get is the derivative of w, or derivative of wi in this case. So this is dwi dt. Okay, is actually proportional to itself. This is true only for that particular sinusoidal function. I mean, it's also true if you plug in cosine. You're going to do the same calculation, but except for imaginary part, you have a real part, right? So as long as you have a sinusoidal function, you plug it into the differential equation, the time derivative is actually proportional to itself. And if the time derivative of something is proportional to itself, what does that mean? It's going to be an exponential growth or decay as a function of time, right? The simplest possible dynamical system we can have is ddt of something equal to a proportionality constant times itself. And now somebody look at this proportionality constant and tell me, do I have an exponential growth or decay? It's decay, right? Well, except for when this thing is equal to 0. When my 2 pi k delta x is actually exactly to a multiple of 2 pi. What does that mean? What happens if 2 pi k delta x is actually equal to a multiple of 2 pi? Well, of course, there is a case where the function is constant when k is equal to 0, right? When k is equal to 0, the function is constant, and I'm not having a decay of any constant function. But what if 2 pi k delta x is actually equal to 2 pi or 4 pi or something like that? Well, what if 2 pi k delta x is equal to 2 pi? That means k times delta x is equal to 1. What can somebody visualize that case? What's the grid spacing? What's the function like? So that's actually the case when delta x is the period of the function, which means no matter if it's a cosine or sine, my grid points, remember in finite difference, I only remember the value of the function at the grid points, but what if my grid points is spaced every period? That means on this finite difference grid, I cannot distinguish whether I have a constant function or a sinusoidal function. I have no idea what the amplitude of the oscillation is because I'm sampling every period. My grid is too coarse for that function. Right? Similarly, when 2 pi k delta x is equal to 4 pi, my period is actually half delta x. It's just too much coarser. Right? So basically, what I'm seeing is that I have exponential decay for all the functions I have any hope to resolve. Right? For all non-constant functions, the grid can resolve. Well, but another consequence is that I cannot hope to be resolving all functions. And for things, for example, I know I cannot have I have no exponential decay for functions that have period that is equal to the grid spacing. What if the period is just a little bit larger than the grid spacing? Then the decay rate, although non-zero, is going to be very close to 0, right? And that's one way of thinking in extremes, right? I know I have no decay if k delta x is equal to 1. If k delta x is slightly larger than 1, I have some decay, or it's slightly smaller than 1. I would still have some decay, but very slow. That's very different from the analytical rate of decay, right? For analytical function, the higher the k is, the faster the decay. While here, it's not the case.